over here, we have triangle ABC, which is equilateral, and suppose that within the interior of the triangle, we choose a point P and connect a perpendicular from P to each side of the triangle, called the lengths H1, H2, and H3. Now, I want you to find the value of H1 plus H2 plus H3. Now, on the surface, this might look like some random geometry problem. However, the answer will teach us a very interesting fact for all equilateral triangles. So, let's delve right into it. So firstly, the thing that makes this problem seem counterintuitive is that this point P is not fixed. Sure, other than the fact that it's within the triangle, there's nothing to really define that point. So it seems like that this value should not be fixed. But it is. So what is that value? Well, maybe you might try considering angle chasing and maybe perhaps performing trigonometry. But that is not going to be very effective if you were to actually try it. So how can we come up with another approach? Well, if thinking about one-dimensional quantities is not going to be sufficient or effective, then maybe try thinking about two-dimensional quantities. Check this out. So consider this. I'm going to connect from each vertex to the point P with a line segment. So we're going to connect the segment BP, we're going to connect the segment AP, and we're going to connect the segment PC. Now, I'm going to let square brackets denote area. So for instance, the area of APB will be denoted like this. So that's the area of triangle APB. So APB. Now, I want you to consider the quantity area of APB plus area of APC plus area of BPC. What is this quantity? Well, notice that these three triangles, APB, APC, and BPC, if you were to look at the diagram, notice that these three triangles literally piece together to form the area of the entire equilateral triangle. So this quantity is just equal to the area of ABC. Cool, right? Now, notice this. What's the area of triangle APB? Well, for APB, we have a base length of 10, right? And times that with the height, h2, you get 10h2, but you have to divide by 2. So that gets you 5h2. So we can write this area as 5h2. So that's 5h2. And notice that for APC, similarly, we have, there's a height h1 and a base length of 10. So that's 10h1 and then divide by 2. So that's going to be 5h1. So notice that we're just writing the areas of these three triangles in terms of h1, h2, and h3. So for BPC, that's h3 times 10 divided by 2. That is 5h3. So 5h3. And notice that we can divide both sides by 5. So we get h1 plus h2 plus h3 is equal to the area of ABC divided by 5. However, ABC is a known triangle. It's an equilateral triangle with side length 10. And there are a million ways in which we can get the area of an equilateral triangle, given its side length. It's something that becomes second nature once you do a lot of geometry. However, I'm going to get the area in a way that I think everyone should understand. So consider this. We have an equilateral triangle, right? Now, consider this. Okay, consider this. Consider dropping the altitude from a vertex down to the base, right? Now, because it's an equilateral triangle, this altitude is perpendicular and it cuts the base at the midpoint. So each segment is just 5, right? So that's 5 and 5. And because this is it's a right triangle, right? Well, the hypotenuse is 10, this is 5, let's call the height h. Then we can find h using Pythagorean theorem. So we have h squared plus 5 squared is equal to 10 squared. And we get that h is equal to the square root of 75, or 5 root 3. And to find the area, we just take the base times the height divided by 2. So that would be the base, 10, times the height, 5 root 3, divided by 2. This is equivalent to 25 root 3. So the area of our triangle ABC is 25 root 3. So this value over here, well, that's 25 root 3 divided by 5. That would be 5 root 3. So that's 5 root 3. And notice that we've solved our problem. We have the value of h1, h2, h3. Or there's some, at least. So it's fixed. It's always 5 root 3. Isn't that cool? Now, notice what I basically just proved over here. Okay, forget about this condition that it's 10, okay? We have an equilateral triangle, and we're going to call its altitude, right? Its altitude h. Then, in a very, very similar manner as we did with this problem, you can prove that h1 plus h2 plus h3 will always equal to the height of the equilateral triangle. And this isn't something that I just discovered. This is a very cool theorem with a name. It's called Viviani's theorem. Notice that if I were to bring back the condition that the side length is 10, then the altitude of this equilateral triangle is 5 root 3. We got it over here, right? So it's true for the case when we have an equilateral triangle with side length 10. In fact, this would be a proof for Viviani's theorem because you can scale this length with any factor to get all equilateral triangles. Or of course, you can just repeat the process by setting this side length to be x and then just, going through the entire algebra. You will eventually get that this is true as well. So the point of this video, though it was to show you a cool problem, was also to show you a very nice theorem. Anyways, I hope you enjoyed this video. I hope you found it interesting. If you did, then please consider dropping a like and subscribing. Thank you very much. Bye.